So today I'd like to present our proposal for a secure transport for remote direct memory access. And the main reason for that is RDMA is becoming more popular in the public clouds. Right now, you could rent machines and have access to RDMA capable devices. And since the RDMA becomes more available and actually the prices are going down, we can see an explosion in the number of the systems which take advantage of RDMA networking. And this is just some names of the systems which were published in Top System Conference for the last 7 years. And they actually choose RDMA networking for lower latency, higher bandwidth, and lower CPU utilization. But unfortunately, we would like to point out that they all sacrifice security, as current InfiniBand stack doesn't offer any secure transport. And just to explain, just to give a small hint on how secure InfiniBand architecture, I'd like to invite you to read the paper from Rothenberg et al. So they implemented 6 different attacks on InfiniBand architecture and as well as implementation of InfiniBand architecture. But here I'd like to focus only on the vulnerability V8, which was the lack of a secure transport. And as you can see, the half of the implemented attack were related to the absence of a secure transport. But actually, the absence of secure transport just didn't appear in 2021. It was a problem for the for the many years before. Actually, it was first mentioned in the RFC 4297 in 2005, and then was even proposed a solution around that time to have some small changes to InfiniBand architecture to enable secure transport. But of course, unfortunately, this solution wasn't feasible, and it was a bit naive, and of course, it was not adopted. But this problem was for a long time, and even in 2017 on the Mellanox forum, there was a question about secure transport for InfiniBand, and Mellanox simply replied that it's a challenging problem and it wasn't solved yet at that time. And actually, in August 2020, there was first known to us a device which offered secure transport for InfiniBand architecture. It was IPsec over Rocky. And we will discuss it today later, why we think this is not a good solution. But I'd like also to mention that there was a recent paper from Google, which actually implemented their own architecture with RDMA capabilities that only implemented the secure transport. So they didn't even implement a plain transport, they just implemented secure transport, which shows that there is a need for a secure transport in industry. Right now, I'd like to explain what a secure transport is. So secure transport is a communication transport which offers the following 4 capabilities. Integrity and authentication, I think the most famous one, the integrity assures that the packet is not changed by an adversary during the transmission. Authentication allows the recipient check who was the sender of the packets, as well as encryption, which allows you to hide the content of the payload which transmitted through the transport. And finally, which is one of the important and I think the most challenging one, is the protection against replay attacks, which allows which prevents an adversary to inject traffic or replay the traffic which it captured before. And you may wonder right now, okay, this is probably not so difficult capabilities. Can we already implement as an application level that has happened in TCP when we first had TCP and then somebody implemented the top something like TLS. But unfortunately, RDMA was designed to be completely offloaded to the network controllers. And then if you look, for example, at one-sided RDMA reads, the target machine, it's not even the CPU of the target machine, it's not even involved in the packet processing. So there is no way application could actually make some protection. So for the one-sided operation, it's clear that that has to happen on the NIC and not by the host. So application level is not possible. So you could say that we could limit it to two-sided communication to the send-receive, that it's still possible. Yes, we can have some primitive scheme, but I think first of all, people choose RDMA for high performance, and then nobody wants to pay this penalty by the application to pay for this these overheads. And the second thing, that even if we make this naive encryption scheme, it wouldn't be possible to have full protection because an adversary could just inject a lot of packets in the NIC, which would consume all the posted receive, and then you would have a denial of service on the connection, which would break it. So that's why we cannot do it for two-sided communication as well. So we think that InfiniBand architecture is an urgent need for a secure transport. That's why we propose SRDMA, which is a lightweight security extension to existing InfiniBand architecture. So it uses symmetric key because it's the fastest cryptography algorithm available. And also we have all these capabilities which I mentioned earlier, and we have protection against all possible attacks which are related to these capabilities. I think what is the most important that our change is backward compatible with existing InfiniBand architecture, and it can be easily adapted by the all InfiniBand architecture, including native InfiniBand and all the versions of Rocky. Right now, I'd like to talk from application view. So from the application, we think that for the SRDMA, we need only just small changes. We propose a new connection type, which we call secure, reliably connected Q-pair. So from the verb perspective, it would be a new Q-pair secure connection, which you create where you provide attributes which specify the key, which should be used for the encryption, as well as security codes. In our existing implementation, we implemented various codes which offers different protection. So it can be just protection of the header, so it's source authentication, or protection of the whole packet, which provides integrity. Or also we can have encryption the payload to have secrecy. And we have different algorithms. So from the application point of view, you don't need to change your application. So you use the same verbs API when you submit your read-write request and all possible requests. You just change the part on establishing connection when you just specify that you need not RC but secure connection. Right now, I'd like to move to the packet format. So in general, all the InfiniBand base packets have the following format. We have some routing, then we have base transfer header, payload, followed by the checksums. Right now, you could have a solution from Mellanox, which offers IPsec over Rocky, and the whole idea that you encapsulate your Rocky packet inside of the IPsec packet. So this is IPsec packet, and it's not even aware what is inside of its communication. In our solution, in SRDMA, we make security as a part of existing protocol, and our secure header is an extra header after the base transfer header. And what is good about this approach? So our packet is still like InfiniBand-based packet. We don't change routing. We completely rely on the routing which is offered by InfiniBand-based protocols. And also we reuse the same checksums, and we just add this security header. And I think here I'd like just to give you a brief overview, because you may wonder what is different in this solution. So you should remember that IPsec is a network layer security. So since we need to encapsulate something else, we have larger headers. In SRDMA, we just need to add message authentication code. Also, IPsec only works for Rocky v2, and our solution works for all the protocols. What is more, since IPsec is not aware of what is sending, it doesn't know about Q-pairs, it doesn't know about memory access, you don't have additional features which SRDMA provides. I will present them later during this talk. And finally, since IPsec is network layer, you install instructions per IP. So it should be done by your administrator, so you do it on the OS level. You install policies how the following not following connection, but following path in your network should be encrypted. In SRDMA, you install policies per Q-pair, and which is done by the application, which allows the application to manage its security.
Konstantin, we have a couple of questions here.
Okay, yes.
Have you looked at Secure XRC?
At what? Secure?
XRC. Mark is asking the question.
No, actually, no.
Okay.
I'm not familiar with this.
Okay. And do you have any plans to propose this extension to IBTA?
Yes, that's one of the plans. So yes, that was a research project when we made the paper, and that's the part when we will try to engage the community in adopting our protocol.
Okay, thank you.
So actually, my first question wasn't expressed very well.
Sorry.
You're doing SRDMA extensions for the RC QPair type. Have you considered doing the same extensions to the XRC QPair type?
No, actually, we didn't look at XRC. We focused on RC, only on reliably connected. So yes, so right now I'd like to jump back to the changes to the packet format. So from the application, you saw that's not a lot of changes, but from the packet format, as we said, we just add a small header, which actually contains the message authentication code. And to indicate that we have this header, we decided to reuse 3 bits from this reserved part of 7 bits, which is highlighted in red stripes. And depending on the value encoded in these 3 bits, it says what is the size of the message authentication code after the transfer header. So if the value is 0, it means it's an old packet where there is no message authentication code. And if there is it's at 1 bit, then it's 96-bit size of the message authentication code. And then you could see other sizes in the table. And actually, this 512 is a quite huge message authentication code size, which would be enough for the next 1,000 years. And that is extremely unlikely that we would need more bits for securing our packet. So this is solution for years. I mentioned before that we need a protection against replay attacks, and how it is done right now in all the protocols, that you make each packet unique. So you, in your calculation of message authentication code, you just simply add a unique number, which gives unique tag to your packet. And in most of the protocols, they just reuse current sequence counters of the protocol. So in our case, we first look at the InfiniBand, and in InfiniBand transport, we have just 24 bits PSN. And unfortunately, if we look at the current speeds of the devices, these 24 bits get reused after 80 milliseconds, which implies if we would do this with these 24-bit counters, we would need to have connection reestablishment with a new key each 80 milliseconds, which is not practical. That's why we propose a simple solution to the problem. We extend packet sequence counters to 64 bits, but only on the end host. But between end hosts, we communicate still 24 least significant bits, which can be reused by the InfiniBand protocol which would stay the same for the InfiniBand protocol, but that just the counters which are used for the security, they're 64 bits. And then actually, when we transmit least significant bits, this is enough to understand the full 64-bit counter, which was used for packet protection. And we can do that as InfiniBand architecture ensures for the reliable connection that the sequence numbers are growing sequentially. So here is a simple scheme how we actually calculate the MAC. If we'd like to have source authentication, we just calculate message authentication code over the routing header, base transfer header, when we add this unique nonce. If we'd like to provide protection for the payload, we include the payload in our MAC calculation. And of course, if we like to have secrecy, then we also can encrypt the payload and write the MAC accordingly in this our secure header. So right now I'd like to show you the overheads compared to the IPsec. So this is the overheads of storing keys on the device. So here it is the same. But for the nonce counters, we need to store less because we can reduce existing counters of InfiniBand. Whereas IPsec, it would need to, since it encapsulates ROCE, it needs a separate counter that it used in the protocol. As well as since we just small extension, we just need to store this message authentication code when IPsec needs actually to have the whole IPsec header, which is 32 bits, the smallest size that's if we have transport IPsec, but for the tunneling, the header is much larger. But that's not where we stopped. So we actually proposes a new concept of secure protection domains. As you know, protection domains exist in InfiniBand architecture to have some resource sharing between trusted and Q-pair connections. So Q-pair connection can share some resources. We propose to extend it and have so-called secure protection domain. And the core idea of this protection domain that we can actually install one key in the protection domain and use this key to derive key for each connection. So actually, we don't need to provide keys for each connection. We just can provide one key for the protection domain, and the individual keys will be created on the fly with pseudo-random function. And what it allows us, allows the NIC to have only one key and then derive the keys on the fly. And this key can derive at two endpoints using the simple equation. So we just use their endpoint identifiers and then QPN endpoint connections, which allows them both generate the same key. And as a result, when we create connection inside of the protection domain, which is secure protection domain, all the connections will be inherently secure. And in that case, we actually can scale with the number of connections, which is not possible for IPsec for different endpoints. Another feature which we offer, which I just like to briefly mention, this is extended memory protection. So right now in the InfiniBand architecture, memory protection is based on RKey, which is a small 32-bit token that should be included in each packet just to prove that you know about this memory. So we propose crypto-based memory protection. The key idea is that you could use a separate key, which we call memory key, which allows you to calculate a tag, which is we call KSR, given the address you'd like to access. And then you include this token, KSR, into calculation of your MAC. So it allows the recipient to check whether the sender has the particular key. This scheme allows you to have crypto-based memory protection, which doesn't rely on the R key, which is not secure at all. But plus, it enables features as a memory subdelegation, which I'd like to invite you to read in the paper. But the core idea that the server can give access one endpoint, for example, to access 4 GB of its memory, and that machine can decide to subdelegate access to other endpoints without communicating to the original machine. And it can actually limit the access to some part of that region. You may think that this all the security schemes is quite convoluted, but not. Actually, the whole packet processing can be visualized in this simple diagram, which I think you can read it in the paper. But as you could see, all these features and memory protection scheme and the secure QPair is just one small diagram, which was quite straightforward to implement. So right now I can jump to the implementation of SRDMA. So SRDMA was emulated using a smart NIC from Broadcom. It was Stingray APS 225. This NIC is equipped with 8-core ARM CPU, and it has 8 GB of DRAM. And what was important for us that it had crypto acceleration in this ARM cores. The NIC had 2 ports of 25 gigabits, but actually for smart NIC capabilities, only 1 port is available. And since we emulated our protocol, so we did not implement it in the hardware, we implemented it in software, we implemented it on top of Rocky V2. And that's why in our case, the good put was 20.6 gigabits. So that was our line rate in our experiment. And first, before we started implementing, we decided to check the speeds which the CPU provides. And actually, for the most popular secure scheme, we could achieve the line rate using just 2 threads. And what was interesting, for 8 threads, we could even achieve 100 gigabits for AES algorithms. For this reason, for key derivation, in the key derivation, we use AES algorithm as this pseudo-random function. Here is that I need to give some more details on the implementation. So our secure connection in our SRDMA implementation consisted of 3 connections. So we established QPair connection between SmartNIC and their host, as well as we establish one connection between the smart NICs. And here is an example how the RDMA write was implemented. So when the host wanted to send the RDMA write to host B, it first sends the packets to its smart NIC. Smart NIC would add the message authentication code depending on the security level installed. So then it sends it to the smart NIC of host B. The host B would verify the packet, and if it passes the validation, it would write this to the memory of the host B. So that was the basic implementation. As you could see, to send the packet from host A to host B, we had to actually do free message passing. So free, it's not message passing, but basically free communication were involved to just send from one endpoint to another endpoint. As a result, we have higher baseline latency. So here is the plot where we show the latency of source authentication. So source authentication just checks the MAC over the headers, so it doesn't include the payload. That's why we were sending just small packet with payload of 16 bytes. And as you could see, the best algorithm in that case was EAS algorithm, which was adding just 1 microsecond, less than 1 microsecond for write latency, so it was half round trip. And also around 1 microsecond for read latency, which we measured as full round trip. And then we decided to evaluate these additional schemes which we had. This is secure protection domain, extended memory, or if we have combination of both. And in this experiment, we assumed the case when the NIC doesn't have a cache. So this key derivation should happen on the fly once the packet arrives. Actually, for the real implementation, we expect that the NIC would have a cache where it could cache the derived keys. And only in the case if the key is not in the cache, then it would have a derivation. So in our case, there was always derivation, which was actually adding around 2 microseconds for one key derivation. And when we need to derive 2 keys, we had actually a higher latency, so higher overhead for the communication. Then we jump to evaluation of the full packet authentication. And here, as you could see, that actually the best algorithm was fully 1305 for the packet protection. So and the least efficient was hash-based like SHA algorithms. But when we actually jump to the encryption, we actually can see that the best one was the EAS algorithm. And actually, EAS is one of the broadly used algorithm for encryption for high performance setting. That's why we think that is the first algorithm which should be implemented for a secure transport. And I'd like to jump to the bandwidth experiment. This is the LUX experiment which I'd like to present, and we have more experience in the paper. So as you understood, we emulated RDMA. So it was implemented in the software of the smart NIC. And of course, it's ARM CPU, which has von Neumann architecture. We couldn't efficiently have processed the packets, and then we have this whole overhead of memory transfer from the DRAM of the smart NIC to the caches of the CPU. So that's why we had quite high overhead, even for the no encryption scheme. So when we had just one thread, we could achieve only around 8 gigabits per second because of the data movement. That's why we could only achieve the line rate using 4 threads of our ARM cores. And here and then we measured this with encryption, and then we could achieve actual line rate for header authentication. This is as we said, the simplest simple protection scheme. As well, we could achieve line rate for packet authentication for the for some of the algorithms. And actually, we could almost achieve the line rate for EAS when we used encryption of the payload. Then we performed experiments for the secure protection domains, extended memory. But here is, again, we had a scenario when we have no cache. So actually, every packet incurred the miss, and then we had to derive a key for each packet. Of course, in reality, the NIC would, for example, have a miss on the first packet, but then the rest, it would just reduce this key. But in this experiment, just to have different plots, we assume the case that we have packets arriving from different endpoints, and then we have constant misses. or we have just zero cache. And as expected, we have just lower numbers, but anyway, we could achieve the line rate for header authentication and for packet authentication. We performed a similar experiment for the read bandwidth, but we even had a lower bandwidth for the basic case when there is no security at all. So it's just parsing the packets and moving them from host to host. And we here could achieve only around 16 gigabits per second. And overall, we actually had similar results to the write case, but it just was the top bandwidth just lower. Overall, I'd like you again invite to read the paper when we implemented different benchmarks. We integrated our solution to the hard key value store, and when we evaluated our memory delegation scheme. And I think I'd like to say that our solution was just kind of emulation, but we believe it can be easily adopted, easily implemented in the hardware, because there are already papers which shows that on FPGA you could implement ES algorithm and achieve 100 gigabits per second. So that's a place where I can take your question.
There is a question from Vladimir. Actually, Glenn, I'll start with Glenn's question. Glenn, feel free to ask, actually. If you're here, I'll just start and feel free to pipe up and add your comments. For IB RDMA example, please clarify adapter SmartNIC Connect X and or is it Bluefield 2? Have you tested those?
No, we had only, as SmartNIC, we had only Broadcom. So we didn't use Bluefield because we don't have it.
Okay. For the IB example also, it was a, or was it all Rocky?
So it was all this Broadcom and it was on top of Rocky V2.
Thank you.
Yeah, and Vladimir comments saying it's an interesting approach. There is also need for datagram-based connections.
No, so we focused on the part so we focused on reliable transfer. So datagrams for the users are available on the unreliable case, and then we think that it's doesn't make a lot of sense to have unreliable and secure. So if you have secure, you kind of imply reliable, and that's why we focus on reliable and didn't focus on datagrams. And then in datagrams you don't have RDMA. And the focus of the work was to have memory access using read and writes.
Thank you. Any other questions?
So if someone was interested specifically in Rocky mode, but not interested in InfiniBand, what would be the advantages of using SRDMA over IPsec?
So yes, that we had I think one of the disadvantages that if you look at your traffic, if you'd like to analyze traffic in your network, you would see that only the here is IPsec traffic, and you even would be sure what is inside. It could be some TCP, it could be some application, but here, first of all, you allowed for traffic analysis, you would see that this is InfiniBand. This is RDMA. You could easily understand it in your analysis. And plus, as we said, you have this extra feature. So as like this trusted protection domains, also applications are responsible for security, not the OS, and all these extra features.
But if you map it into a cloud domain and you have applications running in virtual machines that don't trust the cloud infrastructure, you wouldn't want the contents of the packets to be traffic snooped anyway, right?
I think on that perspective, this is similar solution. So encryption happens on the NIC, so you trust your PCI Express bus in both cases, and then encryption happens there. It's just let's say different order of the encryption how it happens. So we do it at the transport layer, they do it at network layer.
Okay, thank you.
Any other questions? Okay. Thank you, Konstantin. Thanks for your time here today.
Yeah, thank you.